In this video, we're going to begin talking about the cross product, which is similar to, but less useful than the dot product. We talked about in the previous videos the dot product and orthogonal vectors. So talking about the cross product, we're asking ourselves, can we take two vectors in R3 or 3 space, and can we find a third vector which is mutually orthogonal to the two? All right, so this is useful to us, but it is a little bit more limited than I said than the dot product because, again, the cross product only works in R3. It is only defined in R3. So I have a picture using our right-hand coordinate system. And you can see we have two vectors, u and v, and this cross product is the orthogonal vector, or the vector that is orthogonal to both of them. So if I'm able to place u and v in the same plane, then I can find a vector that is mutually orthogonal. So let's talk about the definition. We're going to talk about it one way. And then we'll move into a different definition that we'll use in a minute, but this is going to kind of help us develop our thought process. So here's one definition of the cross product. Say that we are starting with two non-zero vectors in space. We're talking about u and v. Two vectors are parallel if one is a non-zero multiple of each other. So if u and v, these two vectors, if they are not parallel, then they determine a plane. They form a plane such that some scalar multiple of a plus some scalar multiple of v, that is a sum. So these two vectors are in the same plane. And essentially what we're going to do is we're going to select this n vector, which is normal or orthogonal to the plane, using the right-hand rule. So n is a normal unit vector. It is perpendicular to the plane that u and v are lying in. Unlike the dot product gives us a scalar output. The cross product is a vector. So here's my definition. U cross v equals the magnitude of u times the magnitude of v times sine n times that normal vector. Remember, sine, we always associate that with y, so that makes sense for us to think about this as a vertical extrapolation out, and that's why we have sine in here. So I want to emphasize this symbol. This is u cross v. This is kind of bigger than a multiplication symbol traditionally would be. It's a cross. The cross product, u cross v, is the vector product. Another way to call this cross product, that vocabulary word there, we can say it's a vector product. U cross v, this normal vector that's extending up, is orthogonal to both u and v in our R3 or R3 space. It is a scalar multiple of the unit vector n. So one thing we want to notice is that this method, we're required to know this angle theta, right? And there is another method we can use which doesn't require the use of theta. And we're going to come to this shortly. So now that we have defined what a cross product is, let's talk a little bit about some properties of the cross product. One property that the cross product tells us about is, whether or not vectors are parallel. So if you will remember from a previous section, we said that vectors are orthogonal or intersect at right angles if their dot product, u dot v, is equal to the scalar of 0. So if u dot v equals the scalar 0, we know that two vectors are perpendicular. Here we're talking about parallel. So as long as we have two non-zero vectors, we can say they are parallel if and only if u cross v equals the vector 0 or the 0 vector. All right. One thing that says if and only if, so that's a biconditional statement, which means that the left implies the right and the right implies the left, or the first and the last, however you want to think about it. So if you know that the cross product of two vectors is equal to 0, you can assume also that they're parallel. The cross product also obeys a few of the following laws we have here. So if we're given three vectors, u, v, and w, and then we refer to r and s as scalars. If we have the scalar r times u cross with the scalar s times v, essentially what we see is we can factor those two scalars out because those were both multiplication, multiply them in front, times that cross product. U cross the sum of v and w, essentially that cross product is distributing u cross v plus u cross w. V cross u is equal to the negation of u cross v. And I think that's important to notice or note. That's also letting us know that u cross v is not equal to v cross u. So the order matters when you're calculating this cross product. In my opinion, 4 is essentially the same as 2. V plus w cross u is v cross u plus w cross u. The 0 vector cross the u vector is equal to the 0 vector. And this one we use a bit. U cross v cross w is u dot w times v minus u dot v times w. And lastly, we have one more rule we're going to talk about before we do examples in the following video. Here we have the magnitude of u cross v. And the magnitude of u cross v tells us the area of a parallelogram. Since n is a unit vector, the magnitude of u cross v, is the magnitude of u times v times the sine of theta. And really, we want to think about v times the sine of theta as giving us that height. So a parallelogram is a rectangle, and if I took this little piece of the rectangle and slid it over here, it'd have a nice, perfect rectangle. So the area of a parallelogram is just base times height, like any regular rectangle. So the base here is u, and my height is the vector v times sine of the angle. That's giving me vertical. Remember, sine is always associated with the vertical coordinate. So the magnitude of u times v sine theta times n, the magnitude of n being the normal unit vector is just going to be 1, so we don't need that there. So we can essentially see that u cross v is magnitude of u times magnitude of v times sine theta. And that's why we defined the initial cross product in this way, because it helps us to see this definition and why u cross v is the area of a parallelogram. So in the following video, we're going to talk about the determinant formula, which helps us to solve u cross v. And we can use that when we do not have an angle, which will be most cases that you see.